Hi there, and welcome from Ventura, California to Cutting Edge Applications of Unmanned Systems Technology, sponsored by Novotel and Inside GNSS, and hosted by WebAttract, the leaders in thought leadership webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they showcase cutting-edge applications of unmanned systems. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation today during the Ask the Expert panel session with both of our panelists. Now, we've invited you, along with over 400 professionals from 43 countries and 30 states and provinces, representing a variety of industries. Over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Now, before we do get started, Richard Fisher, Director of Business Development at Inside GNSS, would like to take a moment to welcome you and introduce our main moderator for today. Richard?
Thank you, Lori. On behalf of the Inside GNSS team, including our editor, Glenn Gibbons, and myself, I extend a hearty welcome to our international audience for today's web seminar. In just a few minutes, we're going to hear some fascinating descriptions of using unmanned systems to support precision farming applications and for remote inspection of far-flung infrastructures. Steve Waslander and Ian McCrae will describe the GNSS positioning and navigation technologies and techniques that they use to meet the operational requirements of these very demanding applications. But before we begin, I just want to explain Inside GNSS's approach to our web seminars. We limit ourselves in the number of web seminars that we offer each year in order to allow the time needed for preparations to ensure the high quality of the content and presentations by our panel of experts. I believe that you'll find that today's event provides an excellent example of that approach. Now, I want to turn the webinar over to today's moderator, Demos Gebre-Egziaber. Over the years, Demos has helped develop and moderate numerous Inside GNSS webinars, and he's especially close to today's topic. In his day job, Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota Twin City campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, his work is focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments, including the use of such systems on unmanned vehicles. Demos, we're delighted you're here today, and we thank you for joining us again for today's event. Demos?
Thank you, Richard, and hello, everyone, and glad you could join us today for this webinar. Before we get started, we'd like to take a quick poll of the audience to kind of break the ice. So, Lori, can you put the poll up?
And folks, coming up on your screen is that first poll. We'd like to know from each of you, currently, which of the following industry or operations has the most users of UAS? And this is based on the number of applications to the FAA for a Section 333 exemption. So do you think it's agriculture, real estate and aerial surveying, utility inspection, or emergency management? So it looks like our front runner, 45% saying agriculture, followed by 36% saying real estate, aerial surveying, 10% utility inspection, and 9% emergency management. So Demos, any surprises
there? Well, let's see. Kind of, and I'll answer that on the next slide. So let's go ahead and actually get started here by talking about who's using UAS, and that kind of sets the stage for what our webinar is about today. So this table here is taken from a study done by AVSI recently on the number of applications for operation permits or exemptions by different applications in the U.S. And as you can see, aerial photography and real estate are at the top, and agriculture is at number 5. However, this is not the entire story. As you'll see from today's webinar, different applications require different types of technologies in their unmanned aerial systems, and in the case of agriculture, there is a compelling case to be made for using these vehicles in agriculture, but there are still issues that need to be dealt with and addressed, and so in the future this table might change and agriculture may be at the top. Also, the other thing about this table is the majority of the applications here were for using multicopters. And as you'll see from today's webinar, it turns out that multicopters are not always a solution for agriculture applications. So with that, went too far here. Let me get back. What I'm showing on this slide, just to put things into context, is a fixed-wing UAS that's used for precision agriculture applications. And in today's webinar, what we're going to hear from our two panelists are about the two key sensors seen here. The first panelist, Ian McRae, is going to talk about what the payload, the cameras, are used for in precision agriculture and how they're used. And then our second panelist will talk about the algorithms that go into the flight control system that is required for doing precision agriculture or remote infrastructure monitoring. So as we move forward, basically these are the three questions we want to answer in today's webinar. One, what is precision agriculture? There's a lot talked about it, but the details of it are not really widely known, so we'll try to get that across clearly today. Second, what role do UAS play in precision agriculture? And the third, what are the technologies, what are the challenges that must be dealt with before we have a turnkey UAS solution for precision agriculture and infrastructure inspection? So these are the three things we'll try to answer in today's webinar. So with that, let me introduce our first panelist who will be presenting, and that is Dr. Ian McRae. Ian McRae is a professor of entomology and an extension entomologist at the University of Minnesota Northwest Research and Outreach Center. His interests, research interests, center around the spatial and temporal distribution of insects within field of crops, colonization, seasonal distribution, and environmental effect on insect mortality and movement. The work involves the use of digital mapping, spatial statistics, remote sensing, and the use of unmanned aerial systems as platforms for detecting and assessing the geographic distribution and associated effects of insect infestations. He received his PhD in entomology from Oregon State University. Ian?
Thank you very much, Demos. With the population expected to exceed 9 billion by 2050, we're obviously going to have to increase our food production. And because we're limited by the amount of arable land that's available, most of that increase is going to have to come from efficiencies. Balancing these efficiencies, ecological sustainability is going to become increasingly important, although it's an imperative now. One of the methods whereby we try to address that environmental sustainability is through currently integrated pest management. Now, integrated pest management is the application of pesticides only when they're necessary. The application is linked to trigger thresholds that maximize economic return while decreasing unnecessary pesticide use. However, it still involves treating an entire field rather than just spot treating. Where we're going is to precision agriculture, and specifically in my field, that would be site-specific pest management, which is a part of precision agriculture. Now, precision agriculture is the targeted application of agricultural chemicals, not only when they're necessary, but where they're necessary within the field. And that relies on a very high-resolution digital mapping of pest populations in the fields. For example, the map that's up there now shows the distribution of aphids that are colonizing a seed potato field. And those dark pink areas, the darker the pink, the heavier the aphid populations. And what we've found in our research is that aphids have a tendency to colonize the edge of the fields first, and we find that they're there for 10 to 14 days prior to moving inside the field. And this provides the producer a 14-day period in which he can target applications just at the edge of the field instead of treating the entire field. Now, this technique has been adopted by a number of growers in our area, and what we find is that they can have the same control with of aphid pests using only 17% of the insecticides, which is obviously both an economic and an environmental benefit. However, the trick is here, you have to know where the pests are. You have to have detailed information of their distribution within the field. And that is time-consuming. That map was constructed using ground research. In other words, we had researchers out actually surveying the entire field. And it took about 16 man-hours per week to do that. That's only a 40-acre field. Now, crop scouts have to scout basically around 15,000 plus acres per day. And so what we see is to produce that real-time data that would be used in detailed mapping that would facilitate precision ag, that ground ground sampling is just not going to be efficient enough. And of course, it would only result in you looking at part of the field every time you went out. So we need to find a faster method of data acquisition for this to actually be implemented. And one of the potentials is remote sensing using Canopy reflectance. When you use Canopy reflectance, in other words, the reflection of various wavelengths of incident light coming from the sun, you can get a whole field assessment of pest populations in a much shorter period of time. And the basis for this is that plants don't use all of the wavelengths from incident light. For example, some wavelengths that are used in photosynthesis, for example, are reflected like green, the green wavelength, which is why plants appear green. The thing that makes this useful for remote sensing, however, is that stress induces changes in plant physiology and in structure. So insects, disease, weeds, drought, these all result in a decreased chlorophyll level. Now, chlorophyll is in chloroplasts, which are small organelles that are inside of cells. And specifically in plants, they're in these palisade parenchymal cells. Now, the palisade parenchymal cells are right underneath the leaf cuticle up on top. Now, as stress decreases the amount of chlorophyll that's in that plant, those palisade parenchymal cells will start to change structure because the chloroplasts, where the chlorophyll is housed, start to denature, and so the inside structure of the parenchymal cells is changed, and you end up with a structural difference as well. Now, this is important because chlorophyll absorbs red light, and the parenchymal cells themselves reflect near-infrared light. And this is a wavelength that's just above red wavelength, then it's invisible to the human eye. But what that means is, if you have less chlorophyll, if you have a stressed plant, they're going to reflect more red light and a lot less near-infrared light. And that makes it relatively straightforward if you have sensors that can see those wavelengths to identify stressed plants within a field, especially compared to healthy plants. In this way, potentially infested areas within fields can be identified. This is just a diagram showing the spectral reflectance, or the actual amount of energy that's being reflected in each one of those wavelengths. And it compares a healthy plant, that nice green line, to an unhealthy plant, a canopy from an unhealthy vegetation, and that's that red-brown line. And as you can see, there's a slight dip in the red in the healthy vegetation and a very high reflectance in the near-infrared. In an unhealthy vegetation, you see a much lower reflection in the near-infrared. So consequently, it becomes, like I said, very easy to tell the difference between the two in a field. Now, the balance between red and near-infrared can actually be compared. The ratio can be compared, and it's used to create an index, the Normalized Difference Vegetative Index, or NDVI. And this is probably the most common of many vegetation indices that are calculated using various relationships in various wavelengths of reflected light to kind of assess plant health. And basically speaking, the higher values of NDVI, the healthier the vegetation is. So we can actually use this to look at how stressed a plant is because of an insect population. And in fact, right now we've used this to look at soybean canopies infested with soybean aphid. Now, soybean aphid is an introduced species. It's the most important insect pest in soybeans in the north central states, and it's also the target of a large collaborative precision agriculture project that we've been conducting at the University of Minnesota. And what we see is there's a significant negative relationship between the values of this normalized difference vegetation index, which is on the y-axis. The higher that is, the healthier the plant is, and the amount of aphid feeding over time, which we express as cumulative aphid days, number of aphids on a plant over time, which is basically a measurement of stress. And as you can see, as that stress increases, as that x-axis goes out, that NDVI value drops fairly significantly. So we can use these tools to assess whether or not plants are being stressed by insect populations. Another example of this would be to look at sugar beet root maggot. Now, sugar beet root maggot is a very important pest of sugar beet production in the United States, and it's a very difficult insect to actually get a handle on to look at populations within season, simply because it's feeding on the roots of the plant below ground. These two photographs show false color near-infrared images taken from a camera that's sensitive to the near-infrared, and the brighter the color, the more infrared is being is being reflected by the plants. And you can see the plants that are in the plots in the top picture. Those are from, that's in a plot that has very low sugar beetroot maggot populations, and you can see a lot of near IR being, near infrared being reflected. They're very healthy plants, but the plants that are in that, on the bottom picture, they come from plots that have very high sugar beetroot maggot populations, and those plants are quite duller. They're not reflecting the amount of near infrared, and therefore they're just not as healthy. And so again, we have a good example that you can use this technology to actually sense whether or not you're seeing stress within the field. Now, while the sensors to detect these changes in crop canopies have been available for many years, recent advances in small unmanned aerial systems that can function as platforms for these sensors has made combinations of the two technologies into a usable tool for the application of precision agriculture. And UAS fills a niche in remote sensing platforms. Now, previously, we've used a number of other platforms. Satellites have been used for a number of years, and they're undoubtedly the most economical platform to use to gain this data. They have a very large footprint, a large field of view, but they're not very immediate. If they pass over and you happen to have a cloudy day, they're not going to get data, and you really can't bring it back tomorrow. Airplanes, on the other hand, are much more immediate, but they're expensive to purchase, they're expensive to maintain, and they require either having your pilot's license or hiring someone who does. On the ground, you may have someone who's walking or running a four-wheeled vehicle over a field and scouting, but again, very, very small footprint of information, not very cost effective, and it's very slow. Now, unmanned aerial systems provide an economically, can economically provide the immediacy of that data acquisition, and they do so at an appropriate footprint for precision agriculture for use within a field. There's a variety of sensors that are used to evaluate canopy reflectance. There's cameras that are sensitive to visible and near infrared light. There's thermal sensors. There's spectral radiometers, which actually measure the numerical value of energy that's being reflected in individual wavelengths. That's what was used to get those spectral curves earlier. And all are used to assess canopy reflectance. Most of our applied work focuses on the use of multispectral wavelengths, multispectral cameras that are sensitive to some visible wavelengths and some wavelengths into the near infrared. Our research involves considerable plot work, so we have a tendency to utilize multi-rotor UAS. We like to have the ability of hovering over the plots to ensure we get good data. However, in applied agriculture, we're going to see probably less use of the very small UAS, probably larger unmanned aerial systems, and they're much more likely to be fixed wing because they have fewer motors, get a better result from their power. They basically stay up for a longer period of time, so they have greater flight time, use less fuel, and are a bit more economical. There are also a number of systems to optimize GNSS in these small UAS. A common method is using the signal-to-noise ratio to optimize positioning. On the northern Great Plains where we're doing our work, satellite reception is generally not a limiting factor. We usually catch a lot of birds. And the positioning resolution on the units that we fly is estimated by the manufacturers to be between 1 and 1.5 meters. And operationally, it's actually very close to that. It's a little coarser, but it's actually fairly close. The resolution of the camera sensors is often in the range of centimeters or sub-centimeters per pixel. Higher resolution cameras such as the Sony NEX, which is basically just a modified digital camera, it's been modified to see into the near infrared, has 16 megapixels. They provide very, very detailed visual information. However, there's a catch to that. There's a trade-off, and that's that the higher image resolution may actually equal increased blurring if you're taking your images at speed or if the UAS is moving quickly. So the special built near-infrared cameras such as the ADC Tetracam, which is an older camera that was manufactured specifically for agriculture, usually they have a lower resolution to avoid that blurring issue. Now, altitude at data acquisition also influences your image resolution, obviously. Flights at higher altitude have a larger field of view, so they give you a larger footprint, and they also offset some of the problems with high resolution cameras and still provide detailed information. But of course, your altitudes are going to be limited when you're using UAS by FAA regulations. Now, from an applied viewpoint, we actually have much more resolution in our sensors than we currently need. the most advanced application equipment, the equipment that's actually spraying on the pesticides, still applies to an area that's not smaller than a meter squared. Now that's undoubtedly going to change, but limits of existing application technologies means that the data that we're receiving now is well ahead of what we need for the foreseeable future. Even moderately advanced current small UAS have relatively well-developed and full-featured mission planning software. Many simply use Google Maps to establish flight waypoints that can then be uploaded into the vehicle. Flight telemetry is usually displayed and available for downloading as the flight's ongoing, and this can later be used in orthorectifying the data, putting the images into proper orientation and assigning geocoordinates to the data points. Now, because the sensor orientation, how that camera is pointed when it's pointing down, is very important in acquiring good data. It's just like taking any other picture. You need to have the camera pointed in the right direction. We tend to design our flight plans to accommodate a 40 to 50% overlap in imagery to ensure we capture the complete surface of the field of interest. And this is in case there's a gust of wind or something which changes the attitude of the aircraft. You want to make sure that you're still going to get usable data. In a fixed-wing vehicle, the camera and gimbal is often inside the vehicle, and consequently the roll, pitch, and yaw of the vehicle is often that of the camera or the gimbal. In rotor UAS, the gimbal generally hangs beneath the vehicle, and that means while the gimbal is stabilized and it does compensate somewhat for attitudinal changes of the vehicle, if you have a gust of wind or other environmental input, it may move the vehicle off a stable attitude, and in these cases, the telemetry data that's coming from the actual vehicle may not be useful to orthorectifying those data. So we generally also include a small USB digital accelerometer or GPS unit as well, and we attach these to the gimbal platform of the sensor itself to provide at least a coarse resolution attitudinal data for sensor position. And the time signals from these instruments need to be synchronized with that of the vehicles, and basically it ensures the attitudinal data matches. So as I had said, we look for overlap in our images, and as you can see, as that vehicle moves and acquires imagery, you're going to see a lot of repetition in there, and that's not necessarily a bad thing. The analysis of image analysis is usually a fairly complex and time-consuming computing-consuming process, and the software generally looks for commonalities in the images, what we call tie points, to actually stitch it together into a mosaic. And we can actually do certain things that actually will assist in that. We actually position in the field what are called ground control points, and these are individual patterns, usually on stakes that are elevated above the canopy, that the software then can identify and use as tie points, as stitch points, and put together the image into one large picture rather than just a bunch of multiple pictures. Because if you are stitching those images together and getting one large image for the field, it really does facilitate your image and your data analysis. And this also is where your altitudes may come in. If you decrease the number of images from a higher altitude, economically you'll see an advantage because there's a savings in fuel, there's a saving in flight time, and also there's a saving in post-processing if that's how you're doing your stitching. Again, the regulatory issues, there's FAA operational ceilings that are going to come into it, and of course also data resolution is important. You don't want to get too high or you start to lose resolution in some of your data, and you need to have, again, some positioning ability. However, like we talked about with the application data, your application resolution is about a meter squared anyway. Well, in summary, a lot of the application in precision ag is really being driven currently by vehicle and sensor development, and both of these are developing at an exponential rate. The vehicles and the sensors are changing annually, if not sooner. Adoption is happening very, very quickly, and as the FAA regulations and allow future use, I think we'll see both individual producers using small UAS and focusing probably more on visible data. And there's already a developing industry which is based on spectral reflection as well. And the industry is using usually larger vehicles and more standalone vehicles. There's software and interpretation is still a bit of a bottleneck. It's slower than the hardware development, and especially the stitching stitching software and interpretation software. The interpretation still requires some specialized training. And of course, the regulatory changes proposed changes by FAA are on the horizon for adoption and will probably provide a lot of commercial and private opportunities. The one bottleneck that we, particularly in my lab, are working on is that the diagnoses of pest problems are likely are still a little problematic. I mean, we can tell stress plants, however, we really are still working on being able to tell the difference between what those different stressors are. And eventually, I suspect what we'll do is we'll end up with symptomological models. In other words, it'll take into account not just reflectance data and perhaps thermal data or remotely sensed data, but also environmental conditions, seasonal timing, and things like that to actually come up with a symptomological model for, it'll be a 95% chance of soybean aphid and perhaps only a 60% chance of it being a disease. And that's, I would imagine, where it will go. Either way, we are going to see an increased use in this technology in precision ag, and although we've been talking about precision ag for years, this is probably the most hopeful we've seen as a drive towards seeing this as a reality. Demos?
All right, thank you, Ian. So with that, let's take a pause here and start, I guess, addressing some of the questions that the audience may have for our two panelists. So with that, let's go and bring up our first question here. And this question would be for you, Ian. And it has to, it's basically, would the altitude you fly at have a bearing on how accurate a plant diagnosis of stress can or cannot be made?
Well, actually, that's a very good question. Obviously, the higher you get, the less resolution you have. However, you also have problems flying too low. If you fly only say a meter off or several meters off the crop canopy, a lot of your reflectance data is going to be influenced by leaf structure and by stems, open stems and soil. And so if you fly just slightly higher, you get a much more representative picture of crop canopy and plant health. And there's been a number of papers that have indicated that and optimal altitudes at which to obtain data. Certainly our flights at anywhere between 30 and 40 meters are very appropriate, and many people are flying at that 500 foot 400-foot FAA ceiling and still getting very good data as well. The higher you get, obviously, the larger the footprint, but the less resolution you're going to get. So there are trade-offs, yes.
Okay. All right, so let's see. This is a second question, and I guess I could address it to either Steve or Ian. I'll start with you, Steve. And it's basically, do you have, even though you haven't presented yet, and you'll present shortly, do you have any rules of thumb as to when multi-copter would be appropriate versus a fixed wing for, I guess in your case, precision agriculture and infrastructure inspection?
Absolutely. So the fixed wing versus multi-rotor question really boils down to the range of mission and the loiter time you need in terms of being able to collect the data you're interested in. So the fixed wing obviously has a minimum speed, and therefore you have to take that into account in terms of what you're trying to collect. So for inspection tasks, they're often not the right platform, whereas they do provide a significantly longer flight range. And so if you're surveying a large field, for example, they then become the predominant choice.
Ian, do you want to add to that?
No, it's Steve's spot on. It depends on your application, and obviously, like I'd said, the fixed wings are going to allow you a longer flight time. They're going to allow you a less fuel, but at the same time, they're going to be restricted in that they cannot loiter over a target at all. So if you need detailed information or you need to do a close-up inspection, they're not going to be appropriate.
Okay. All right, so this next question is for, I guess would be for you, Ian. privacy is really an issue with, or is it really an issue with precision agriculture? Have you heard anything from farmers, for example, as to whether they are comfortable with the idea of a neighbor buying a UAS and being able to fly and monitor their fields, et cetera? I mean, is this something that you're thinking about now? Is it too far in the future, or can you say anything to that?
No, actually, I've had discussions with producers. There are some who are concerned about that. Who are a little anxious about it. However, a lot of this technology is so new, and the products are so new to them, that a lot of the producers are of the opinion that there's not an awful lot of difference between driving past the field and actually having an aerial view of it. Also, there's a number of commercial entities that the businesses are actually selling the service. Mostly they're using Visible to look at things like stand establishment, things like that. But a lot of the times they'll make a large flight with an airplane over an entire area, and they'll subdivide the data out, and certainly that's the same model with satellite services. And so you can subscribe to a particular area, and sometimes those areas overlap. From our point of view, yes, there is a concern about privacy, and we fly all of our research flights on university land because of that. Just to make sure that it isn't an issue. So.
All right. Let's see. Now, along those lines, I guess in addition to privacy, liability is also an issue that comes up. So, is it? I know neither one of you is a lawyer, but can you say if there's any factors into how you design the operation of sensors or precision agriculture missions that that would become a thing to consider? I guess I'll let Steve say something about that, and I'll ask Ian to do it to answer it later on.
Sure, yeah, and I'm definitely not a lawyer, but my thought on this is that since we're currently still restricted to line-of-sight operations, in the same way that we require autonomous driving cars to be a liability on the driver, we require the operators to take responsibility for all the actions of their aerial vehicles while they're under their purview. So this will maybe become a much bigger issue as we move forward, to the domain of delivery drones and autonomous surveys of agriculture and inspection sites where operators are no longer in the loop, at which point there'll have to be safety critical guarantees on performance and reliability of the autopilots.
Is there anything you'd like to add to that, Ian?
Yeah, although, as Steve said, I'm not a lawyer either, but I was at a meeting where one was talking about just this issue last week, and in the United States, anyway, the privacy laws that exist actually extend to UAS, and there are also privacy laws that cover private aircraft as well, flying over someone's land. Those laws are actually in place. There's some technological answers to privacy issues as well. Certainly from a commercial application, there's such thing as geofences where you can, preset the vehicle not to exceed a certain limit, and actually even for the photography not to go over a certain limit. So there are some technological responses and answers to it, and I strongly suspect we'll see a lot of those implemented when a lot of these industries start in a full-scale manner. So.
All right. Let's see. Next question. This one is let's see, for Ian, and it's can you say anything, or what is the weather conditions needed to get meaningful result? Is there an issue of I guess cloud cover, sunlight, those kind of things on how this plant reflectance measurements work? And
yeah, there certainly are. From a strict research point of view, and from looking at reflectance, you want to have roughly the same light conditions every day that you're flying. So we fly our missions, our data missions, between 10 and 2, which is at the solar zenith. We fly them when there are 70% cloudless skies, so we're having roughly the same amount of incident light that's striking. However, from an applied viewpoint, we're going to end up in a situation where the data is needed, and it's going to be needed now. I think we'll probably start to see a lot of uplook, downlook sensors, in other words, upwelling, downwelling sensors that can actually compare the percentage of available incident light that's being reflected, and there's certainly a lot of work that's being done on that right now as well. So there will have to be some technological issues that will have to be kind of addressed with before this is implemented on a large scale, certainly the reflectance. Like I had said earlier, there's a lot of information that you can get from visible wavelengths, and that's certainly being utilized right now. And that's probably where most of the companies are focusing at the moment. So yes, there are certainly considerations of sunlight and what weather conditions you need.
And I don't want to steal some of your thunder, Steve, because I know your presentation following is going to talk a little bit about this issue, but can you say a little bit, at least as a motivator for what's coming?
Sure, yeah. Speaking from a computer vision perspective, so a lot of the sensors that we can use to improve our localization accuracy on board these vehicles include the use of computer vision, either IR or RGB type information. And those, what they require essentially is consistent conditions. So if you're trying to use information during one flight, it gets challenging when there's large variations in the illumination that you observe. I've heard a good example of actually rooftop inspections being done at night by multi-rotor UAVs simply because the IR conditions there, in order to detect leaks in the roof surface, are more visible at nighttime. So they're actually doing nighttime operations here in Canada and are working towards doing those in the US as well.
All right. So with that, let's stop the Q&A for now, and let's go into the second part of our presentation. And before we do that, let me just take a second poll. So Lori, if you could set up the poll.
Sure. Second poll for today: from a guidance, navigation, and control perspective, which are key challenges for small UAS avionics? And in this case, we're asking you on the honor system to select your top 2. So is it reliability, size, power requirements, ubiquitous operation, or cost? Looks like we have 57% saying reliability, 18% size, 47% power requirements, 25% ubiquitous operation, and 36% saying cost. Demos, any thoughts on these?
All right, so the second part of our presentation is going to actually talk about our webinar. Is going to talk about some of these issues and look at actually the issue of ubiquitous operation, as well as, I guess, to some extent, reliability. So with that, let me introduce our second panelist here. Our second panelist is, you've already heard from him, is Stephen Waslander, who is an assistant professor in the Department of Mechanical and Mechatronic Engineering at the University of Waterloo, Ontario, Canada. Previously, he was a control system analyst for Pratt & Whitney. Currently, he's the director of the Waterloo Autonomous Vehicle Laboratory, the WAVE Lab. His research interests are in the areas of autonomous aerial and ground vehicles, simultaneous localization and mapping, nonlinear estimation and control, and multi-vehicle systems. He received his Master's of Science and PhD both from Stanford University in Aeronautics and Astronautics. Steve?
Hi, how are you all? Look, I'm very excited to talk to you today about small rotorcraft and using them for inspection tasks. So my take on the poll was I was surprised that ubiquitous operation wasn't higher up there, and that and certainly reliability falls into that as well. But that's what I'll be talking about today. Really, what we've seen so far in the UAV applications is that there's really 3 dominant civilian applications that are taking the world by storm. So we've got agriculture, real estate, and cinematography, and we've seen all these in the COAs that have been approved to date. What's common about all of these applications is that they're operating primarily in open space and within line of sight of a UAV operator, and this is obviously for collision avoidance issues as well as for accurate positioning using solely GNSS solutions. So the type of information that's available for these vehicles to position themselves and to fly safely currently on board the vehicles is not sufficient to move closer to obstacles and do detailed inspection tasks. But I think that next step is possible, and I think there's hopefully by the end of the talk today you'll agree with me at least a little. I think that we can gain a lot by combining or fusing GNSS solutions with computer vision based relative positioning and mapping of the environment in order to enable things like inspection, as a next wave of applications for UAVs. So to pull this grand vision off, I see quite a few open problems still that need to be addressed. And I split them basically into two halves. The first is the perception side. So here what we need to be able to understand is exactly what the multi-rotor vehicles are doing, or fixed-wing vehicles are doing, so that we need accurate models of how their inputs will affect their motions. We then need to develop these universal state estimators that will enable ubiquitous operation, and then use those same onboard sensors, so vision, laser scanners, whatever the choice happens to be, to construct dense maps of the environment right around the vehicle, and also hopefully enable the detection of other aerial vehicles as the number of these UAVs and drones increases in the skies. Given this much richer perception on board the vehicle, we can then turn towards planning and execution tasks. And so here we need to be able to use those onboard state estimates to precisely control the motion of the vehicles within windy environments, so wind gusts and the large steady state winds as well. We want to be able to plan motion for these vehicles on evolving maps, so ensure that the vehicles can move from point A to point B, even as new information is being provided as the vehicle moves through the environment. We also need to do collision avoidance, of course, to ensure that when other area vehicles are in the immediate vicinity, the collisions don't occur. And the last topic, which I hope to talk about as well today, is the need for range extension, particularly with multi-rotor UAVs. So being able to swap batteries or download information to a ground station or ground vehicle, allowing these operations to persist for much longer than the typical 20 to 25 minutes that we see today. So today I'll only be able to go through about 3 of these ideas, but we do have a bunch of research in the various other areas, so you're welcome to explore some of our work in those areas as well. So I'll talk about the state estimation and dense onboard mapping, as well as give a brief example of some of the work we've done in range extension. So for state estimation using vision, and this is really intended as an augmentation for GNSS-based solutions. So whenever GPS type information becomes unavailable, it would be wonderful to be able to fall back onto vision or and use that as a either more accurate or augmenting system to expand the operation envelope. The task really involves 2 separate components, and that is localization of the vehicle's motion. So localization is basically a relative positioning, and as well it requires mapping of features or information in the environment, so that you can construct knowledge, or so you can construct a map of the environment around you, and use that to improve your localization accuracy. And what happens, of course, is that these 2 goals are somewhat opposed computationally. So localization needs to happen quickly and needs to be a very lightweight algorithm so that you can use it in your control loops for precise positioning of the vehicles, while mapping requires sort of a much more intensive calculation, and therefore leads to more detailed representations of the environment, but happens at a slower pace. And so what we've done in our work actually is build on some existing work called Parallel Tracking and Mapping, which was a paper by Klein and Murray in 2007, which really splits these 2 tasks up. So it performs the localization in an onboard tracking thread, and then performs mapping either off-board or on a background process in order to basically take these 2 pieces and separate them as needed for the computations. And so here's how it works. Basically, we have a robot that observes some feature locations in the environment and constructs a map of those feature positions using a set of measurements to those features. Once it knows where those features are, it can switch into a tracking mode, and that tracking mode essentially tracks just the vehicle's motion relative to those known features. So as the vehicle proceeds through the environment, it starts to lose visibility of those features, and so it has to identify some additional features that it can then add into the map. And once it picks those features to add in, it can send, again, this mapping process off board and construct an updated map, and then proceed along with the tracking with these new features included. And so we can repeat and iterate this process as we proceed through an environment. And of course, whenever we observe features that we've seen previously, we can correct the overall map and improve our tracking accuracy significantly. So all of this is, of course, aided by any information you have in terms of the motion of the vehicle from other sensors, such as IMU and GNSS solutions. building on the work from PTAM, which was really a monocular camera solution used for augmented reality, what we've done is look at the option of including multiple cameras on board the vehicle with wide field of view. So relative to monocular cameras, this is an excellent choice because it allows us immediately to resolve scale, even without overlap between the camera images. It also gives us far better visibility of the environment, which means that we can track even when there are structures in the environment of limited visual information. So, blank walls or plots on the ground that have a limited spatial variability. And finally, the last advantage relative to monocular is that we have robustness to partial occlusion. So it's actually possible for an object or a vehicle or something like that to fly through the images and still have valuable localization information in the unoccluded images. Another solution would be to strap on laser scanners onto our aerial vehicles and use the sort of 3D point clouds, those representative of autonomous driving, as a way to build maps of the environment and perform localization. However, for the time being, these laser scanners are quite heavy and expensive, and so they lead to limited flight times and much larger vehicles, which can be limiting in terms of the applications that they're useful for. So the multiple wide field of view cameras provide similar visibility, but at a much lower payload size and cost. We also get more data and more information. So we have color, we have multiple channels, and intensity, and all of these allow us to do additional tasks such as segmentation and target detection within the scene. And finally, cameras are often already required as payloads for the systems, and so we're hoping to use those same cameras in both the localization solutions and the applications themselves. The drawbacks, of course, are that multiple cameras at high resolutions operating at high update rates result in a very large amount of data, and so we have trouble managing and processing all that data in real time on board the vehicles, and that's really where the research challenge lies. And of course, we're still subject to the same limitations of computer vision algorithms in that we need consistent illumination, we have to avoid motion blur in the images, and feature correspondence can remain a significant challenge, making sure that you're associating measurements from different images with the same points in 3D space. So here's what we've done. We've built ourselves a system which starts from synchronous multi-frame image capture. We pass that into our tracking thread, and this thread can run at up to 100 Hertz on a standard laptop. And what it's doing basically is 3 steps. It starts by taking each of the images and extracting individual features. And in our case, we use fast corners because they're relatively cheap to compute, but it doesn't really matter which ones you use. We then pass corners into a feature matching algorithm, which actually tries to warp the patch of pixels around each individual feature back to the viewpoint from which they were first observed. And then we can just directly calculate a patch pixel error and determine whether or not we're looking at the same feature as we were previously. And since we're only doing tracking, we're only doing this on a limited number of patches, which makes it relatively efficient. We then take each of those correctly corresponded features and we combine them into a localization solution, which essentially relies on nonlinear least squares, but can also employ an EKF or particle filter depending on your preference. So all of those methods are possible. Given that we're moving through the environment, of course, we're going to have to select additional keyframes, and so we do this based on metrics that decide whether or not it's time to add a keyframe, and we can pass all that into our mapping thread, which is a large-scale bundle adjustment optimization, and we're using the open source G2O library to do this. So what this is doing essentially is simultaneously optimizing both the vehicle motion through the environment and the feature point locations within each of the keyframe images. And so this constructs a large map for us of feature locations and the current vehicle position that we can then use in the tracking thread to perform tracking updates at high frame rates. So let's take a look at this in action. So here are some results from an indoor flight test at our collaborators lab in McGill University. And so what you're looking at here are the 3 images from an onboard an octocopter. And so each of the dots in those 3 images are actually features that are currently being tracked in the MCPTAM tracking thread. So these features basically have different colors based on what resolutions they were observed at. So some of them are at low resolutions, some are in high resolutions. We're essentially using an image pyramid to construct these various features. And then in the bottom left here, you can see the ground truth compared to the solution that we're getting from our non-overlapping field of view MCPTAM. And so what you can see right at the bottom is you can actually see the accuracies that we're tracking our position with. And this is relative to this ground truth, which is captured from a Vicon indoor positioning system. Basically think a motion capture studio as you would have for cinematography. And so we're seeing on the order of 1 centimeter errors and sub half a degree in orientation accuracy throughout that video, giving you a good sense for the kind of accuracies we can get when the features are reasonably close. So these features are all within about 2 meters of the vehicle itself, and so we get significant or very nice performance from the actual MCPTAM solution. We've of course taken this outside as well to get a sense for how well it works outside. And here we're comparing solutions between MCPTAM and with both overlap and non-overlapping cameras. And so what you can see here is that all the features are significantly further away. So here we're using 4 images instead of 3. And that results in that further distance to all of the feature locations results in a larger error in the positioning solution. And so this gives you an idea for where this vision-based localization actually complements GNSS really nicely, in that when you're out in the open, you've got excellent satellite visibility and you can rely on your GPS solutions. And then as you get closer to objects and have good vision information, you may tend to lose some of those satellites. So the two are a very nice complement and will work very well together once combined. So out here we're seeing errors on the order of about 1 meter and up to 2 to 3 degrees of orientation error, and that's highly dependent on the fact that all these features are so far away from the vehicle itself. We've also been able to actually directly control the octocopter using the MCPTAM solutions. So here we are traveling from waypoint 1 on the ground, so performing a takeoff maneuver upwards to waypoint 2, and then proceeding along a trajectory through waypoints 3, 4, 5, 6, and then landing again. And you can see that at each of these waypoints in the air, once we've established reasonable localization accuracy within the vision threads, we're getting really nice performance in terms of position hover on the order of 10 to 15 centimeters of error in our positioning accuracy. And here we're only using that vision-based solution for control of the position. One other thing you'll notice, of course, is this large deviation upon takeoff. And what's happening here is we've got a very rapid variation in the relative position of the features that are observed. On the ground, you only see features at the horizon and very close to you in the grass. And then as you take off, you see more and more of the ground, improving your positioning solution, but providing an instantaneous error in the actual tracking of the position of the vehicle and causing a major deviation. So these are problems that we hope to address in the future, but what we're seeing is very nice performance once we're established in flight in the air. All right, so given that we can get better and better at localizing in ubiquitous operation, the next step is to try to construct maps of the environment and actually use those maps for collision avoidance. And so here I'm showing some preliminary work that we're doing in simulation to actually using those same multiple camera viewpoints and the same information about the relative baselines between the cameras. We can actually construct accurate 3D representations of the environment. So here we have edges being extracted from gradient information within the images, and so we have 3 of these images operating here, and each one of them is constructing and estimating depth to all of those green pixels in the scene. So this is starting to get to the point where we can actually use those maps for collision avoidance and for route planning through cluttered environments. So the last topic I wanted to talk about today is the idea of range extension using UAVs and UGVs. So this is moving into the execution and planning phase of the tasks. And what we're looking at here really is finding ways that we can actually do precise relative positioning between an aerial vehicle and either a ground vehicle or a moving boat deck. So these can be performed with high-end GPS solutions, particularly RTK type GPS with 2 to 5 centimeter accuracy is really what you need to do this without vision. But what we're hoping here was to again augment our vision, our GPS solutions with vision-based operations. And so what we're looking at is fully autonomous docking on moving targets, essentially. So we can localize relative to the moving ground vehicle by including a target on the ground station, ground vehicle, and then track that vehicle for the landing operation. So this would of course enable significant new applications. So it allows us to do long-term management of agricultural fields, autonomous pipeline and transmission line inspections over longer ranges, remote exploration with aerial vehicles, and even iceberg tracking or wildlife monitoring, which is a pretty exciting application. So this is the way it works. Basically, we start from a GPS-only solution. So we get the position in GPS coordinates from the target vehicle. That allows us to perform a rendezvous operation, which gets us to within range of the vehicle for visual acquisition. We then proceed with an acquisition and identify a target on the vehicle platform and use GPS control throughout that process. But once we've got the improved visual relative position information, we can then perform the entire landing operation using vision only. And this allows us to avoid issues such as the relative errors between two GPS receivers, as well as magnetometer issues when we're operating near ships or large vehicles with significant metallic structure. So we have one last video here for you demonstrating this indoors. So we have an Aztec Pelican vehicle with a Intel Atom board on board, and that's enough to give us 320 by 240 images at 25 hertz, which we can process for the April tag, which is that tag that's located on top of the ClearPath Husky ground vehicle. And so you can see that the Aztec Pelican is actually able to track that tag reliably through flight. So there's no other connection between these vehicles. And it's able to position itself relative to the ground vehicle with sufficient accuracy to fully execute a landing procedure. We've also tried this outdoors, and of course here one of the other open problems comes into effect, and that is the precise positioning of the vehicle in wind gusts. And so what we've observed is as we're moving outdoors, our relative positioning accuracy degrades simply because of the larger forces that are caused by the wind in the environment. And so we're not quite able to track significantly long enough in order to execute the landing maneuver. But as we improve our ability to predict wind gust disturbances, we hope to improve that controller performance and finally execute those landings. So just to summarize briefly, we've talked about 3 topics really today. So the idea of onboard motion estimation and map construction using cameras as an augmentation system for GNSS, giving us up to centimeter accuracy at close range and sub 0.5 degrees. And we've also talked about how multi-camera configurations can really improve the overall performance of these systems. And finally, we talked a little bit about extending missions using autonomous ground support vehicles and coordinated landing operations to make those things possible. And so with that, I'll pass it back to Demos.
Thank you, Steve. All right, so before we move on to the last Q&A session, a couple of things. First of all, I guess this webinar itself and PDF of some resource of lists will be available on the Inside GNSS webpage after the webinar. And in case you want to contact any one of us, myself, Ian, or Stephen, our emails are also available on this slide, and they'll be available for download on the document that will be on the Inside GNSS website. And so before we go off to the last Q&A, let's do one more poll. And if you would put up the poll, Lori.
Happy to do it. Final poll for today. In which of the following unmanned system operating domains are the PNT requirements most stringent? Is it air, land, marine, or perhaps it depends on the operation? All right, so folks are saying 39% are saying air, 12% land, 6% marine, and 43% depending on the operation. Demos?
I'll tend to agree with the folks. It depends on the operation. I guess some air, some land, some marine, depending on the application, could be really challenging and stringent. But again, an interesting spread of answers. All right, so with that, let's move on to the last Q&A session here, and let's start, I guess, getting questions to both Ian and Steve. Let me look at, let's see, so this one is for you, Steve, and the question is about the method of localization that you presented. And the question is it much more advantageous than just using an IMU, especially when you're operating indoors?
Well, yeah, absolutely. The IMU so roll, pitch, yaw, and potentially acceleration information as well. Whereas the vision-based solutions actually give you a full state vector. So they give you position of the vehicle, velocity of the vehicle, all relative to the environment, of course, and as well as estimates of the IMU. So combining the two is actually one of the best of both worlds. You get accurate orientation information from the IMU. You get that corrected or improved with your vision, and then in addition, you get better, you get actual position and velocity information. And that applies both indoors and outdoors.
Okay. All right, so the next question, let's see, going back to the precision agriculture application, and this one is for you, Ian. And the question is, what has to occur to make, I guess, the use of UAS in precision agriculture economical?
That's a good question. The software and the hardware, certainly the vehicles and the sensors are coming along very, very rapidly. There are some bottlenecks to software and the interpretation. I think at current use, the widest adoption currently is using visible wavelengths. However, I think perhaps the low-hanging fruit on the technology and the adoption in precision ag is very likely going to be in crop scouting, and of course in specialized crops. I mean, there's a lot of use of this right now in viticulture and grapes and high-value crops. But I think even in field crops, the most rapid adoption is going to be in crop scouting, where rather than going out and looking at an entire field, a crop scout will have available an image of a geo-rectified image, and he'll have geographic coordinates to go out and actually ground truth certain areas that are identified as stressed. That's probably getting very close to being economically viable now. To continue on and start looking at diagnosis, that's going to be going to need more research.
Right. All right, so this next one is going to be for you, Steve. And the question is, can you say anything about collision avoidance in the work you've been doing, or is any advances or anything you'd comment on in that area?
So collision avoidance boils down to two topics, really. There's collision avoidance relative to transmission lines and structures in the environment, as well as air-to-air or vehicle-to-vehicle collision avoidance. So on the former, we're getting better and better at constructing these 3D maps in real time. However, it's still very data intensive, and there's been a few interesting research labs around the world that have demonstrated onboard collision avoidance on slow-moving multi-rotor UAVs. So that's really starting to get interesting, and hence some of the focus of the work we're doing is in that area. For the collision avoidance vehicle-to-vehicle, the big challenge there is really the relative speeds and the detection ranges which are required. And so there's many different solutions here, sonar, vision, radar, but none really that apply well to the small UAS community. So it tends to be either too expensive computationally or too expensive, period. So making it hard to actually find a good solution for that. So I'd say that part is still really an open question.
Right, thanks. All right, coming back, I guess this one I'll pose for you, Ian, first, and then if Steve has something to say, he could jump in. But it's the weather issue again, and the question is, can you say something about wind and rain, and how this would affect your ability to assess stress in plants when using UAS?
Well, wind and rain certainly shut us down with regard to spectral reflectance. The advantage to, so it's very similar to any of the other platforms. I guess the advantage of UAS over some of those other platforms is the immediacy. You could come back tomorrow if the weather is clear. But certainly we're constrained by the same weather conditions that constrain other platforms. If the incident light is being blocked, then we're not able to record reflectance. With visible work, it's a little with visible data, it's a little different, and then it's a matter of whether or not the weather conditions will allow flight. But I have known that, for example, up here in northern Minnesota, it's very flat. We get a lot of spring flooding, overland flooding, and I know that they have been used by a number of private operators to assess the level of flooding on their own property, and oftentimes they've done that in not very heavy rain, but certainly slightly inclement conditions. So as far as visible is concerned, yeah, you'd be constrained by the same conditions that would limit flight. But for spectral reflectance, yeah, we're constrained as the same as any other platform is.
Okay, and maybe I might be reading a little bit into this question, but for example, if you're looking at a plant that's wet versus a plant that's dry, would the reflectance change? Maybe that's part of the question that's being asked, I think.
Yes, yeah, and that actually is true as well. It's one of the other reasons why we make our flights, at that solar zenith. So it's an opportunity for the dew point to rise and make sure that the plants are dried off. But yes, water that is sitting on the plant will affect reflection of certain wavelengths. Yeah, absolutely.
And Steve, on the same question here, but from the vision sensing point of view, any things
Sure.
you'd like to add about weather conditions?
Oh, sorry. I was thinking actually on the vehicle platform side, there are small UAVs that are now rated to fly down to -40 degrees and up to 85 degrees and can operate in wind, snow, rain, and sleet. These are vehicles that I've been working with for a while at Arion Labs, and they're building essentially military-grade multi-rotors. So those vehicles can at least perform in all those conditions, including wind gusts up to about 95 kilometers an hour, or I think that's 55 miles an hour. So the vehicles can operate. The question, of course, is whether or not the information gathered is at all useful in those conditions. And I think Ian's got a nice answer to that one so far.
Okay. All right. This one is for Steve, and it's a question about landing on a moving platform.
Sure.
And I guess the question is there any advantage to having a proactive system trying to harness the vehicle that's coming into land, or have you looked at that, or can you say anything about that?
Definitely. If the landing platform is moving significantly, then there's a major advantage to actually harnessing the vehicle. And there's some beautiful examples. I believe it's the Little Bird, which was actually landed on a moving ship deck with a Novatel GNSS solution. And basically what they have is they have a sort of a capture rod that the vehicle deploys that then locks into a grate. And what's going on there is as you cut the thrust to the vehicle, you actually lose the ability to keep yourself on the platform if the platform starts to move. So you want to sort of secure or tie down the vehicle as soon as possible. So in that sense, it's valuable. For the work that we've been doing with the moving ground platforms, we tend to wait until the platform's not moving that much, and only moving in, say, a forward direction. And that allows us to do the landings without concern for falling off once we've landed.
All right, next question for Ian, and it has to do with altitudes at which we fly these things to get reflectance data. And is there research being done to figure out what the optimum altitude to fly at is, and if so, who's doing this kind of research and what kind of thing is going into it? In other words, is there a single optimal altitude to fly for getting reflectance data for different types of stresses?
I don't know if there's a single optimal altitude, but there's been studies done comparing very low and very high altitudes, and also very low and moderate altitudes within just a small UAS. Most of that research is coming out of Europe. There's a group also that we're looking at overall using UAS to map vegetative areas and looking at the limits of it. I believe that came out in last year in 2014, and they had some issues with thermal imagery, and we're looking at thermal data, and that altitude had a large effect on thermal. There's also some effect on, like I'd said, on spectral reflectance, but I think it's more having to do with structure than it is, field structure than it is with light changes. So.
Okay. Let's see. So along those lines, that brings up another question, which kind of, I guess I'll pose for both you, Ian, and Steve. I'll start with Steve. You talked about using visible light for doing your positioning. Is there a way to combine, for example, these sensors that are used for getting reflectance data and using them as a sensor for the localization problem?
Yeah, it is going to be possible. So I actually have an ongoing research project trying to figure this out. Essentially, what we're relying on to do the localization with multiple cameras is a fixed and very well calibrated baseline between the camera centers. And the second you incorporate, say, a gimbaled camera payload, which is typically how the cameras are mounted for the payload operations, you break that knowledge about that specific. However, if you properly calibrate the motion of the gimbal and actually measure it in flight, you should be able to recover the same precision with which we know the calibration parameters on the fixed rigs, and therefore we should be able to incorporate these gimbaled cameras as well. And it's really appealing because these are often the highest resolution and best images that are collected. Essentially, you spend your whole payload on getting the nicest sensors you can in the air.
All right. Let's see. Next question for Ian. Can you say anything about what the business operational model for Precision Ag would be? Would each farmer own a UAS, or would some service provider operate them? Maybe Steve could also pipe in for the infrastructure inspection. Do you know anything? Have you heard anything about the operational scenarios? I'll let Ian start.
The answer to that is yes. You're going to see both. We're going to see, we already are having individual producers who have their own small UAS and are flying them, and most of that, as I'd said, is probably they're looking at visible data. So they're looking at stand establishment. They're looking, a lot of them will use it to look at their irrigation ditching and plot where they want to ditch a field. So there's a lot of application just from a producer level, but there's also a burgeoning industry that's starting up using much more advanced vehicles and much more advanced sensors. And the business model is, there's a number of different business models whereby the data is transmitted either by the cloud or actually sometimes by the vehicle back to an industry's location where they actually will do the analysis, the image analysis, and send out some recommendations and the images back to the producer with some interpretation. There are some people who are basically selling the service to existing data that you gather data using your own sensors in your own vehicles. So there's a number of different actual business models that are starting to accommodate the industry applications for precision ag. And it's being adopted by the larger companies as well. It's being tied into auto steer and a lot of the the onboard GPS, and so there's a lot of work being done at basically all scales of industry, right all the way through to personal use.
All right. On the infrastructure inspection side, anything you want to add to that, Steve? Or
Yeah, it's very much the same thing there. Essentially, the very large infrastructure companies are setting up their own GIS departments with UAVs and looking at, specific solutions to their particular inspection needs. And then the smaller players or inspections that are only required on a yearly basis are often being done by second-party or third-party operators, people that are buying UAVs and then building all the tools necessary to do the inspection inspections and deliver reports essentially with potential problem locations and actionable items for the owners. So again, I think we'll see sort of a large mix of what's going on. What's nice about it is that it's really a data problem, and so once the data collection has been streamlined, it's possible for anyone to buy one of the platforms and operate them conveniently. Then the software will do the rest of the processing for you. So it's one of those things that can be owned individually going forward.
All right, so you said something in that answer that is a key word for the next question, so I'll pose the next question for you. You said that I guess each user kind of looks at their own needs and tunes it to their own needs. With respect to the the navigation and localization you've been working on, how much tuning is required, or is the solution you have a turnkey that would work on every application?
It's not yet a turnkey, no, and this is sort of the need of this ubiquitous operation is really that it becomes such. But as you probably know, vision-based solutions often require very careful analysis of the lighting conditions and the exposures in order to avoid things like motion blur and illumination issues. There are interesting research projects going on in all these areas, essentially, working on the illumination invariance properties that are available from multiple camera threads, so you can actually convert these images into things that look almost the same under very different lighting conditions, and then extract features from those images. So there's definitely some really interesting stuff going on in terms of robustifying the image solutions so that they'll work in a much wider range of conditions. But my take on this is really that when we combine these vision-based solutions with GNSS and IMU data on board the vehicles, and also with sonar information for altitude or laser ranging, we get this sort of robust suite of measurements that we can use to correct and evaluate the different sources of information. And I think that's going to lead to sort of quality monitoring or integrity monitoring of the localization solutions.
Okay, let's see. Next question for Ian, and I think you've probably alluded to this already in your talk, but I'll pose the question because it's asked. Do you think the ultimate goal with precision agriculture is to treat each individual, I guess, plant or cornstalk as a individual patient? Is that, and do you think we'll ever get there? Or is that even a good thing to do?
Well, I don't think we'll get there by next week. But the idea is there that we're already working on machine language between UAS and ground-based robots, which will go up a crop row and side dress nitrogen or apply a herbicide or a pesticide based on information that's coming to it from an eye in the sky sort of thing. And I mean, there are a number of projects already working on that. There's a number of them that are working on them in corn and on row crops. There's one working in citrus down at University of Florida. And so there's this is definitely where people kind of see long term where the kind of science fiction of agriculture is going. However, science fiction has a tendency to turn into science fact with the development of technology. So is it going to happen immediately? No. Is it beyond the realm of possibility? Absolutely not. It's very possible that we could end up there.
Right. Next question. This one, let's see. I'll direct it at you, Steve, first, and Ian, you could pipe in afterwards if you have comments. What kind of endurance, what kind of battery range do you get out of the UAVs that you fly currently?
Sure. So the best ranges we've seen so far are on the order of 40 to 50 minutes. These are very lightly loaded systems, so very limited payload, and with basically a giant battery taking up 3/4 of the weight of the vehicle. So those are for the multi-rotor UAVs. Fixed-wing UAVs are much longer range, so an hour to 2 hours is not uncommon. The typical operation for the multi-rotors is on the order of 20 to 25 minutes for well-designed systems, and for those vehicles that are heavily loaded with payload, 5 to 10 minutes is about all we can get. So there's been a lot of interesting solutions proposed to this problem, and I'll just mention a couple of them. One would be to use tethers more often, so we can get tethers out to the order of 250 meters that have only limited impact on the actual vehicle operation and allow you to fly indefinitely. And others are, of course, the idea of battery swapping that I mentioned earlier. So having the vehicle autonomously dock, change its battery, and then take off again. And this has been done in a few different cases already.
Right, and Ian, with the vehicles you fly, what kind of endurance are you getting out of them in your missions?
Yeah, very similar to what Steve was saying. Usually when we're flying a multi-rotor vehicle and we have it loaded with sensors, it depends on the size of the vehicle, but if it's one of our larger ones, we don't get much more than 20 to 25 minutes out of a flight, which is enough for what we need to do. The smaller rotors are even shorter. Some of the smaller quadcopters, we probably get maybe 15 to 20 minutes out of them, and that's with a very, very light sensor load. Other than that, you can go to, there are some gas-powered UAS that's available, usually the single rotor, and there are fixed wings as well. They'll give you a little bit more flight time and certainly have a bit more payload, but again, they're going to be limited to probably within an hour, or at least in our experience they are. So yeah, Steve, we have very similar experience.
Right. Next question. Let's see. This one is for you, Ian. And the question is asked, do you have any success stories using UAVs in improving pest monitoring process or the standard of using, and I guess the questioner says, grunts like me in the field? So.
He's a person after my own heart because, yeah, a lot of the times I am a grunt in the field. Yeah, actually, the one that we're having probably the best results with so far, and it was kind of a not really very surprising, is actually looking at defoliation. And we're particularly looking with Colorado potato beetles and defoliation in potatoes. And this is a very serious defoliating insect. And we'll probably have a publication on that out, probably submitting it this winter. The data has been very good. It's a very close match for actually going out and looking at evaluating the defoliation in the field. And again, this is probably not a real surprising result because you're looking at what's not there anymore, and so it's pretty easy to make an estimate of what your field fragmentation is based on aerial imagery. So yeah, that's probably the big success story that we've got so far, but the rest of them are coming along, and yeah, we've had very good results in a number of different systems, so we're quite hopeful.
Right, excellent. All right, looks like we have time for one more question, so I'll pitch this one at you, Steve. And do the vehicles in your multi-vehicle scenario cooperate from a navigation point of view, or are they completely independent, and do you see any benefit by having cooperation?
For the most part, they're operating independently. So what we've had is on the automated landing, we've done both relative GPS landings as well as relative positioning from vision for landing. But we haven't actually had them communicating GNSS solutions or corrections between the vehicles. And from the vision perspective, again, we haven't had them sharing maps or feature locations in order to have more knowledge of areas they were about to enter, although that could lead to some interesting improvements for a fleet of vehicles, essentially having a scout go out and map the area and then having the working vehicles operate more slowly and more safely, more reliably. But no, we haven't looked at it in great detail yet.
Right. Well, it looks like I guess we may be running out of time, so I guess thank you everyone for joining us today on this webinar, and I think I'll hand it back to you, Lori.
Well, thank you so much, Demos, and before we sign off, we'd like to take just a moment to thank you all for joining us and trust you found today to be of value. Special thanks to Ian McRae and Stephen Waslander, and of course, our sponsor and co-host, Novatel and Inside GNSS. This is Lori Dearman saying, hope we see you on the next one. Have a great rest of the week. Bye for now.